Veo. Vemos. Okay. Group. A ver. ¿Dónde está esto? Ya, correcto. Hello, guys. Thank you for coming on time, every one of you. Let me say hi to the ones I see here. Let me say hi to Diego, to see Diego, Jose, Elias, Brian, Juan Sebastian. Thank you for coming, guys. I'm coming on time. Let's check our syllabus, what we have for today. We have our syllabus here. Okay, so you guys can see this. What we have is, okay, October 31st. We have heat exchanger sizing, tube side, sizing, shell side, shell side. And then from November the 7th, we have separation. And the very last one, we have evaporation. So, okay. So we're going to start, hopefully we start with heat exchanger sizing today. Okay. There's no message. Okay. So we'll go to our PowerPoint slides for today. Let's see if we can share that. Process equipment. Okay, there we go. So heat exchangers. Hopefully we'll cover that today. Tomorrow, this is an exception that we're making for this week because on Thursday, you know, it is a holiday, it's a long holiday. So we're having class tomorrow, just this time, I mean, and then the rest of the weeks is going to be Tuesdays and Thursdays as usual. Just tomorrow because there is a long holiday coming. Then we'll have class from 7 to 8 tomorrow. Okay, so let's go to exchangers. The purpose of this chapter is to introduce the concepts needed to design and determine the performance of typical heat exchange equipment used in the process industries. The emphasis of this chapter is on shell and tube heat exchanger design. In addition, a set of useful working equations are also presented which can be used to design and evaluate the performance of heat exchangers. So basic relationships, counter current flow, the flow configuration between process streams and or utility streams is important in determining the correct driving force for heat transfer. The most common idealized model is a counter-current flow, which is best illustrated in the sketch and the temperature enthalpy diagram shown in figure 21, as we see here. So in here, we see that one of the streams is coming on one side of the exchanger and leaving on the other side of the exchanger. Let's say if this is position 1 and this is position 2, this one is coming from left to right, but the other stream, let's say the hot stream, because we see on the temperature enthalpy diagram or temperature energy diagram, TQ diagram, we see there is a reduction in temperature in a counter current flow on the hot stream. This is a hot stream, that's why you see it in red. And the cold stream, we see it in blue, is coming from low temperature to an increase in temperature. On this drawing, we can clearly see that. We can see that T1 is gaining temperature, but is coming on one side and leaving on the other, while the hot stream is coming on the opposite side and leaving on the side where T1, the cold stream, is coming in. And then there is a delta C where the temperature of the hot stream, dZ, or this small interval right there, dZ, is changing along the distance, as well as the temperature from the cold stream, small tz, that is being increased by the interval delta C along this z-axis, while the temperature of the hot stream is being reduced from the entrance all the way to the exit. So there is a gradual decrease from T1 to T2 on the hot stream, and there is a gradual increase from small t1 to T2. In figure 21, subscript 1 and 2 indicate inlet and outlet conditions respectively. The temperatures of the two streams are identified by uppercase and lowercase letters. For the simple case shown in figure 21, which is this figure, there are no phase changes in either stream. In addition, the specific heat capacities of both streams are assumed to be constant, which gives rise to the linear temperature profiles shown in figure 21. The energy balance. So this is important because this is a simplistic assumption that heat capacities are constant. We will see along this set of slides that there is an exercise that we probably will be doing. I'm not so sure if today or tomorrow or even next Tuesday. Depends how much we are able to cover tonight and tomorrow. It is an exercise where CP now is dependent on the temperature and is no longer constant. So higher temperature gives a different CP than lower temperature. So CP is now a function of temperature. There are many terms that you have to calculate the CP based on the individual calculations of the different terms that the equation for CP has. But we'll see that later on. The first simplistic assumption is that CP is constant, as it says in here. So if so, then you have these straight lines. The slope of the line for the increasing temperature of the stream that is increasing in temperature is going to be straight, and the slope and positive, as you see there, and the slope of the decrease in temperature between the hot stream T1 and T2 is going to be straight, but it's going to be a negative slope, as you see right there. That is the result of a constant CP, a constant heat capacity. Energy balances for both streams are just going to be MCP delta T for the hot stream and MCP delta T for the cold stream. You guys might remember this from fundamentals of heat transfer, so this is a review in a way. Where capital letters are used for the hot stream and lowercase letters are used for the cold stream. The term Q is a total rate of heat transfer between streams, energy per time. So energy per time would be in the SI system like joules per hour or joules per second, which is a watt. When we have kilojoules per second, that would be a kilowatt. So in any case, it's energy per time. Big M as we see there, that's a mass flow rate with the dot. That is mass per time, could be kilograms per hour, kilograms per second. The big M of the hot stream and the small m of the cold stream are the mass flow rates, and Cp and small cp are the heat capacities of the streams. The streams are physically separated, usually by a metal wall, and heat is exchanged to this metal wall. The driving force for the heat exchange is, of course, a temperature difference, big Tc minus small tc. So the difference between the temperature difference of these two, between this one and the temperature coming in here. So the two differences in temperature. Since the flow is countercurrent, we will have a delta T in here between these two and a delta T in here, these two as well. So that will be, if this is position 1 and this is position 2, there will be a delta T for position 1 and a delta T for position 2. If both of them are co-current, they come in at the same port, the same position, then we will have T1 and small t1 and T2 and small t2, and there will be a delta T1 and a delta T2 depending on the configuration of the exchanger. What else do we see here? The streams are physically separated, which is true. You might see them coming in and it might seem that physically they touch each other, or they somehow they form some sort of a mixture or a solution or something like that. But in reality, they are separated by metal pipes, that is metal tubes. That is, one of these streams is coming on the outside of these tubes, and the other stream is coming on the inside of the tubes. In this simple example, probably if we have steam, condensing steam on a heat exchanger, then condensing steam will be on the outside, or as it is called, on the shell side of the exchanger, while water, if we are heating up water, that will be coming in on the inside of the tubes. So the steam and the water do not touch. They just do not mix. They do not touch. They only have an indirect heat exchange so the driving force is, of course, a temperature difference, big Tc minus small tc, between the two streams at the given location, Z in the exchanger. In general, this driving force changes throughout the exchanger, and some appropriate average should be used. In order to obtain a relationship between Q and the inlet and exit temperatures of each stream, a simple differential balance can be written on an element of the exchanger, as illustrated in the right-hand sketch of figure 21. So this is where you see this small element, that is this differential element. It could also be written D, as in David, dz. This is a different, because the delta, that's what it is. This triangle is delta in Greek. We could, in English, that would be D, as in David, dz. Is a differential element. In this case, a differential of the length along the exchanger. If the exchanger is 1 meter, if the exchanger is 1.5 meters, 2 meters, then dz will be a small length, very small length. It could be just a few centimeters, 1 centimeter, I don't know. It could be any length from the position 0, like you see there, to the position where Z is equal to L, the full length. So if the full length is 1.5 meters, 2 meters, then when Z is equal to L, then we will have this differential all the way to the position of L. So, okay, so we're here. And we can see the Q will be equal to UZ. So Q is equal to UA delta T, as we see in there. UA delta T is equal to MCP delta T. So U is the overall heat transfer coefficient. As you see there, is in position C. They're implying that the overall heat transfer coefficient changes along the Z axis. So if it changes, because the area changes. The area changes because as you move along from the position 0 to the position L, the full length of the exchanger, the area will change. As you move from 0 to L, the area will increase because the length of the pipe is going to increase. And if that happens, then dq will change. But if U does not change, then you can just drop the Z and just have the U right there. And this dA represents pi times D. So P area is not pi r squared, as it will be the cross-sectional area. The area is only the wetted perimeter on the inside of the tubes. That is pi times D. That is the inside wetted perimeter where the flow goes through. So it is true that the full pipe is, that the pipe is full of water, correct? So that is correct. But only the wetted perimeter has exchange of heat with the other side where the steam is condensing. So that will be pi times D times the length of the, as you see there, pi times D times the differential of the length along the exchanger. That will represent the area, the wetted perimeter, and not the cross-sectional area. Where big TZ, the hot stream, minus small TZ is the cold stream on a differential length, that's what you see, the Z there, is delta TZ. For many applications, the overall heat transfer coefficient does not vary substantially with the location in the exchanger, and thus U sub C is just U. That is, if it does not change, there are some assumptions, as you know, in engineering, you can make assumptions. That's a beautiful thing about doing engineering. You can solve a problem just assuming certain circumstances and assuming perhaps certain conditions, you know. And then later on, once you solve your example, your problem, you can go back and check if the assumption was correct or if it was just too simplistic, and it gave you actually an error in the calculation. But if it's mentioning that U does not change too much along the exchanger, then you can safely assume that U sub C is just going to be equal to U. That is, U is going to be constant. The overall heat transfer coefficient could be taken as constant. Since heat capacities of both streams are assumed to be constant, as you guys remember in the first slides, we assume in a simplistic model that CPs of the hot and cold streams were going to be constant. For simple examination purposes, so we're going to assume to be constant. And later on, we will have examples where they are not constant anymore. And then we have to make comparisons. How far from the truth are we? How far from a realistic calculation was a simplistic calculation? And that would be good to know. And we hopefully will see that later on, along these set of slides, because it's just, there are many slides in here. So we hopefully, as we cover that, what I don't want to do is just be running through the slides. And then we just probably losing along maybe some, or make, if we go too fast, it might be a bit confusing. So we don't want to do that. We want to go a bit slow enough, but not too slow, just slow enough. Okay, since heat capacitors of both streams are assumed to be constant, the temperature difference between the streams, or delta TZ, is also linear with respect to the amount of heat transfer, Q, as illustrated in figure 2. So we see here, this delta T2 is implying that there was a difference between two streams, between the hot and cold stream in position 2, and this delta T1 is implying that there was a delta T between two streams, between the hot and cold stream at position 1. So it happens in position 1, delta T is higher than delta T2. Okay, as it would be expected. It would not be expected that both were equal. If both were equal, there would be no driving force for heat exchange, as we know. So, okay, it's good to know that there is there is a driving force. There is a temperature and delta T difference between the two positions of an exchanger. Okay, what else we have here? The area under the graph, it could be seen that delta T over delta Q, which is this delta T over dq, would be equal to delta T1 minus delta T2. D delta T over dq will be equal to delta T1 minus delta T2 over Q. Because Q will be X amount of Q or a given amount of Q minus 0 right there. So it's just Q. And in this case, it will be delta T1 minus delta T2 as you see expressed in here. It could also be expressed that the Q, if you move these to the other side and these two are moved to the denominator and Q is moved to the numerator, we will have Q delta T, as you see there, this will be in the numerator, divided by delta T1 minus delta T2. This move around these terms, so we could have an expression similar, an expression like expression 20.4. What is the benefit of that? Well, in expression 20.4, we have delta T over delta T1 minus delta T2. And so it will be, in a way, it will be easier to integrate these in order to solve this equation. Substituting equation 4 into equation 3. Equation 3 is this equation. Substituting the definition of dq into equation 4, substituting that in here, we will have this expression. So this, which is expression for 20.4, is going to be equal to the expression for 20.3, or in other words, this expression right there. You can also see that the subscript Z has been dropped from the overall heat transfer coefficient and also from delta T. So now we have this expression is equal to U delta T dA. Very good. So if this is moved around, these two are going to the numerator on the right-hand side. This one is going to the denominator on the left-hand side of the equation. It's going to look something like this. If we check this, we have delta T, d delta T over delta T right there. And then on the right-hand side, we will have delta T1 minus delta T2 times U dA, as you see right there. And Q is this Q on the left-hand side. So to integrate this from the temperature differential on position 1 to the temperature differential on position 2 of this expression, then we will have, as a result of this integration, we'll have a logarithmic term. Well, it will have to be evaluated between delta T2 and delta T1, pretty much. Now, if this, and that will be equal to U, the integral from 0, position 0 on Z equals 0 to A, that will be just A, as you see right there, times the overall heat transfer coefficient. This differential of, let's say, delta T in position 1 minus delta T, which is a constant, that is a constant, that will be right there on the right-hand side of the equation. Then we have expression 7. I believe this is correct. Yeah. Now, question 7, if this term, the logarithmic term of the temperature differences, goes to the denominator, we will have UA delta T1 minus delta T2, which is a constant of the temperature differences in position 1 and 2 on the exchanger, divided by the logarithmic term of the differences of delta T1 divided by delta T2. So we will have expression 20.8, where this definition, this term of the constant divided by this logarithmic term, is called the logarithmic mean temperature difference, as you see expressed right there. Now, where delta T Lm is known as the log mean temperature difference and is given by these equations. So this is the best way to account for the driving force in an exchanger that flows countercurrently to calculate the logarithmic mean temperature difference along with the overall heat transfer coefficient and the area of the exchanger to determine what is called the heat load, or what is, the heat load of the exchanger, which is Q. For heat exchanger design and performance calculations, the LMTD, logarithmic mean temperature difference, is a correct average temperature to use when the streams flow countercurrently. This is important to remember. It is particularly recommended, let's just say, or strongly recommended when we have a countercurrent flow. When should we have a countercurrent flow? Hopefully as much as possible, because as we will see later on, a countercurrent flow will give us the best heat exchange, the most efficient heat exchange, and will require the smallest heat exchange area in comparison to the co-current flow, the flow where both streams enter the exchanger on the same side. That is called a co-current flow. Okay, so countercurrent flow is just the configuration where it is most efficient in the heat exchange between the hot and cold streams. Okay, so it says, note, for the special case when big MCP is equal to a small MCP, and when there are constant pressure phase changes for both streams, the dT between the hot and cold streams is constant throughout the exchanger. That is, the TQ lines for both fluids are parallel. So we see the definition. This is another way of expressing this. This is, I believe I took this. It says in here, Stephen Hall. So I might have taken that from Stephen Hall. I'll have to check if it was not taken from Peters, Timmerhouse and West. I'm not so sure. I have to check on that. In any case, this is not from Turton, but if you check on this, it is equivalent to this expression. Let's say we check in. T in is the temperature, let's say, of the hot stream coming in Puerto Limpio is outside. T out is the temperature of the cold stream coming out of the exchanger. Minus T out is the temperature of the hot stream coming out of the exchanger. Minus T in, the temperature of the cold stream coming into the exchanger. So doing that, the natural log of the difference between this expression or this difference divided by this difference, this will be the delta T mean, the countercurrent flow. Now, you're also seeing here an F. An F is a correction factor depending on the configuration of the exchanger. And we'll try to cover that today. Most likely we'll cover that tomorrow, because it is important to consider the correction factor. If we have a 1-2 configuration, that is a 1 shell and 2 passes. If we have a 1 shell, 4 passes, we will need to correct for the logarithmic mean temperature difference. So we will obtain this value, this F value, from a graph, and it's very simple to calculate that. And we'll have to multiply that F, the correction factor for the temperature. We'll have to multiply that times the delta T for logarithmic mean temperature difference. And then we will have a corrected value for delta T mean. That is a value that will need to be used in the estimation of the heat load of the exchanger. For such cases, the expression of LMTD gives 0 for what cases? Well, it says for the special case when big MCP is equal to a small MCP. Can you imagine that? That the flow on the hot stream, let's say we have water on both ends. We have water on the hot side, we have water on the cold side. The CPs are very similar because it's just the same element. The flow rates are very similar. We have the same flow rates inside of the tubes and outside of the tubes. Then we have a case where MCP of the hot side is going to be equal to the M or almost equal to the MCP of the cold side. And that will give us 0, that is, this will give us 0 in here over ln of 1. Now, this is like an undefined situation, which is indeterminate, but by using the L'Hopital's rule, it can be shown that logarithmic mean temperature difference is equal to the arithmetic delta T. It shows the difference calculated by a subtraction, an arithmetic temperature difference, not logarithmic mean anymore. But that's only for this case. Since LMTD is simply an average temperature difference between the streams, it should make sense that the average between identical temperature difference is just that temperature difference. There is a arithmetic temperature difference. An alternative flow pattern in the exchanger is a co-current flow. That is, as you see in there, the hot and cold streams are coming from the same side and exiting on the opposite side, both of them. But look, this temperature difference is huge. When the configuration is just, it's like this. This temperature difference is huge, and this temperature difference is very small. On the sketch on the right, we don't appreciate that. We only appreciate that both streams are coming in on the same side and leaving on the opposite side. But here, when temperature versus delta H is plotted, then we see the enormous difference on one, the enormous driving force, because the differences in temperature coming in of the hot and cold stream, and the small difference in temperature on the other side. A similar analysis to that given for the countercurrent exchanger could be carried out for the co-current configuration and would result in equation 20.5, which is, what is equation 20.5? Well, that equation should be, where is equation 20.5? It's not here. So that means, let me check on the book. That means that equation is missing somewhere. That means I have to include that. Yeah. Well, equation 20.5 would be equivalent to this equation as I see it. Would be equivalent to, say, to this equation from Stephen Hall. The reason perhaps, while I'm using, I should have changed this to 12.3, and we're using Stephen Hall's equation for the delta V logarithmic mean of the concurrent configuration. So what we're seeing is the hot and cold streams, the temperature difference, they are coming on the same side, minus the temperature difference coming on the other side of the hot and cold streams, and then the logarithmic natural log of the temperature difference coming in divided by the temperature difference coming out. So that will be the log mean temperature difference of the current configuration. And we don't have a correction factor in here. The average driving force is smaller than for concurrent operation. Therefore, the heat exchange area for a given cube will be higher for concurrent flow than for countercurrent flow. That's important to remember. The heat exchange, the average driving force, which is this delta T, with this formula, this delta T will end up being smaller than this delta T in countercurrent configuration. So if that happens, if we have, in order to compensate in equation, the definition of Q, which is equal to UA delta T logarithmic mean, in order to compensate, if we have a lower delta T logarithmic mean, we have to increase the area so that the product of the area times the delta T logarithmic mean is the same on the concurrent configuration than for the countercurrent configuration. It could be the same, but we need to increase area. That means the exchanger has to have has to have a bigger area, which means a bigger heat exchanger, physically a bigger exchanger. It says also, second, the limiting temperature that either stream can reach is the exit temperature of the other stream. Whereas for countercurrent operation, the limiting exit temperature is the inlet temperature of the other stream. See, so the limiting temperature here will be the exit temperature of this stream. See, the limiting temperature that either stream can reach is the exit temperature of the other stream. That is, this temperature cannot get lower and reach T2. That would be like the limiting temperature. This is, if area were infinite, then T2 would be equal to small T2. If the area of the exchanger were infinite, just humongous exchanger. Also, a small T2 could be equal, the limiting temperature will be big T2, the hot stream, if the area is infinite, and that is a limiting factor. Examples 21 and 22 illustrate this difference. This is Turton chapter 20. A gas is to be cooled from 100 to 45 using cooling water that enters the exchanger at 30 and leaves at 40. You guys have homework. You have 4 problems, and that is due on the 7th, if I'm correct. So you have homework to do over the weekend, and it has to do with your heat exchangers. It says, what is the LMTD, logarithmic mean temperature difference for the heat exchanger if the flow of the streams is countercurrent, is concurrent? How much more heat exchange area would be required for the concurrent exchanger compared to the countercurrent exchanger? For countercurrent flow, the TQ diagram is shown in figure 20.1. So we see that the hot stream is coming in on one side, leaving on the opposite side. The cold stream is coming in on the opposite side, leaving on the one side in position 1. So they are opposite. So this is a countercurrent operation. So delta T in here is 100 minus 40 is just 60 in position 1. And delta T in position 2, or delta T2, is 45 minus 30, which is 15. The log mean temperature difference will be 60 minus 15 divided by natural log of 60 divided by 15, as it is expressing here. And that will give us 32.46 degrees Celsius. For a concurrent flow, the TQ diagram is shown in figure 20.1b. So now we have both streams coming in on the same side, and both streams leaving the exchanger on the opposite side. Here we have delta T 100 minus 30, which is 70, and 45 minus 40, which is 5. That will make 70 minus 5 divided by natural log of 70 divided by 5, which is 24.63. So now you're seeing that in a countercurrent operation, LMTD is 32.46 versus in a concurrent operation, LMTD is 24.63. That is 31.8% larger. That is, the concurrent exchanger area would need to be 31.8% larger, as you see there, than the concurrent exchange area for the same heat duty. So in order to compensate this difference that you see there for the concurrent configuration versus the countercurrent configuration, this exchanger will need to have a 31.8% larger area than this exchanger here. So it's not exactly the most efficient procedure that we can use or operate in an industrial plant. If we're going to use concurrent configuration, that will not be the most efficient way to exchange heat. The most efficient way would be concurrent protocol or concurrent operation. This is just to show this difference, LMTD of the concurrent configuration divided by LMTD, or the concurrent configuration, produces this 1.318 or 31.8% higher. Will need to be 31% higher. The concurrent configuration with higher area to obtain the same results of the concurrent configuration. Example 2. For the streams and flow configurations used in example 20.1, what is the lowest temperature to which the gas stream can be cooled, assuming the cooling water must leave the exchanger at 40? So in this example, okay, so we have cooling water coming in at 30 and leaving at 40, correct? Concurrent operation. And the concurrent operation is the same. Okay, very well. So it is telling us what will be the lowest temperature to which the gas stream can be cooled, assuming the cooling water has to leave at 40. The limiting condition for this exchanger configuration is given when the exit gas stream is at the same temperature as the cooling water temperature. So can you imagine an exchanger? We have an exchanger of infinite area, an enormous heat transfer area, an enormous exchanger. The limiting temperature will be coming from 100 on the gas side, the hot gas, going all the way to 30. While on the cold side, the water coming in at that temperature of 30 and leave it at 40. This is what is this? A concurrent operation. The concurrent operation, it will come from 100 to 40, because in a concurrent configuration, the water leaves at 40, as in the concurrent operation. So, but the limiting temperature changes because it changes the orientation of the water coming into the exchanger. So, for the limiting temperature in concurrent configuration is 30, as we see here. The limiting temperature of concurrent configuration is 40, as we see there. Often in chemical processes, heat exchangers are used to boil or condense streams. When there is a change of phase in either of both streams, the temperature enthalpy diagrams for heat exchangers look different than those shown for concurrent flow. Some examples, yeah, we're seeing there. Some examples are illustrated in figure 20.4. In figure 20.4, the phase change occurs at constant temperature and nearly constant pressure, and there is no subcooling or superheating of streams. Therefore, one fluid is either simply boiling or condensing, while the other fluid does not undergo a phase change. As you can see here, fluid number 2 does not seem to do anything. It has the same temp, but energy is increasing. So what is happening here? This stream number 1 is cooling down, and this stream is probably boiling at the same temperature. So it says in here, stream 1 cooling, and stream 2 is boiling. It is boiling at the same temperature. Why do we know that it's boiling? This is because it's coming from a Q of 0, or we can assume it's 0, to a maximum Q of the scale. So it's gaining energy. And that energy, those kilojoules or BTUs per hour, however we want to express that, those kilojoules are coming from the stream that is cooling down. On the second diagram, we have this situation where it appears to be condensing steam. Why do we say stream? Because it is a high temperature in this scale. You know, it's marking a high temperature on this temperature scale. While stream number 2 is heating up. It came at a low temperature, and it left the exchanger at a very high temperature. So that means this is condensing steam, or appears to be condensing steam, and this is any fluid, maybe water, maybe any fluid, gaining heat. It says in here, stream number 1 is condensing, as it appears, and stream number 2 is heating. Correct, this is heating. On the third diagram, we see that we have condensing steam, probably most likely just like this, condensing steam, and then we have a boiling fluid here. Both are condensing and boiling at their respective temperatures. Because there is no temperature change. And we know that situation happens when we have a phase change. When we have a phase change, the phase change takes place at the same temperature. So that's why we see in C, stream number 1 is condensing and stream number 2 is boiling. For all these cases, the logarithmic mean temperature difference should be used as the appropriate temperature driving force in heat exchanger calculations. More complicated examples exist when both temperature and phase changes for one or both fluids occur within the same exchanger. This results in sensible heat changes and phase changes occurring within the same heat exchanger. We know that Q, when there is sensible heat, no phase change, Q is equal to mCp delta T. When there is a phase change, Q is equal to M times delta H of vaporization. As we know, when there is a phase change, when we're boiling something, we have mass flow rate times delta H of vaporization. For phase change, when there is latent heat that is added to a fluid and making it boil, while when there is just sensible heat, that will be mCp delta T. For example, figure 20.5 illustrates a case where when stream 2 is a subcooled liquid that is heated to saturation, boiled, and then the vapor is superheated using a superheated vapor that cools, condenses, and subcools. Okay. So we could see here, if we check on the legend on the left, it says TQ diagram, as we say, the TQ diagram in which stream number 1 enters as a superheated vapor, which is this position A1, and is cooled to saturation in position A2, is cooled to saturation. We see there is a decrease in temperature from superheated steam to saturated steam. Condenses, we see a reduction in Q, condenses position 2 to position 3. And then it is subcooled position 3 to position 4. While transferring heat to stream number 2, which is stream that you see here in B, that enters as a subcooled liquid, in this position, it is a subcooled liquid, is heated to saturation, right there, position 2, is saturated position, saturated, liquid, and then vaporizes from 2 to 3. You see the increase in Q, the increase in energy from position 2 to position 3. So by then, in position 3, it is steam, and then finally leaves as superheated vapor from position 3 to position 4. Okay, that occurred because of this driving force between these two. The condensing steam, the condensing superheated steam, from superheated to saturated, from saturated to saturated liquid, from saturated liquid to subcooled liquid, and the opposite occurring on the second fluid, from subcooled liquid to saturated liquid to saturated vapor to superheated vapor. Assessing here the dotted lines between A1 and A4 and between B1 and B4 should not be used to determine the logarithmic mean temperature difference. That is, if you do a calculation on this temperature of the superheated stream minus this temperature of the subcooled liquid, then you probably will have an error. And likewise, if you do temperature difference between the same two, superheated stream and subcooled liquid of the second stream, you also have a significant error in your calculation. From figure 20.5, which is this, it should be clear that using a single LMTD, LMTD is logarithmic mean temperature difference, as we know, so instead of repeating that every time, I would just say LMTD. it should be clear that using a single LMTD shown by the dotted line drawn between the endpoint temperatures based on the conditions of the streams entering and leaving the exchange does not provide a realistic or accurate estimate of the correct average driving force within the exchange. So doing this temperature difference between, let's say, A1 and A4 and B4 and B1, that this situation will occur. It will not provide realistic or accurate estimation of the correct average driving force within the exchange. In cases such as this, that is when we have a superheated steam coming to saturated steam, to saturated liquid, to subcooled liquid, in situations like this, it is necessary to divide the exchange into sections in which T versus Q line is a single straight line segment for each fluid in each section. So you see here, it could be taken from here to here as a single straight line, from here to here as a single straight line, and from here to here as a single straight line, instead of this temperature difference along the dotted lines. Also in here, from here to here, from B2 to B3, and from B3 to B4. So that will produce different sections because a line is let's say, the slope of the line changes. The slope is 0 here, then it changes in here. Then we have a negative slope in here. And also in this particular case, the slope of the line has a lower slope than this slope, lower negative slope than this one. So position 2 and 1, they change slowly. Then slope is here is 0. And then position 3 and 4 is a higher in magnitude negative slope in comparison to B1 minus B2. But in any case, it produces segments. As you see, segment 1 is this temperature difference. Segment A, segment V. Segment V will be this difference that is from the position where it is saturated liquid to higher up in Q. Then we have position C. Position C, why do we have B so small? The limiting, let's say the limiting boundary of position B is this change of slope on the second stream. Since there is a change of slope right there, from this slope, it's going positive slope from B. This is a positive slope to slope 0 right there. That makes that we have a broken line right there, a change in slope, and then we have a dashed line there. We also have a broken line here, a change of slope, and we have a dashed line there. So we have this segment, segment V. Also from this position to the next position where the line is broken, which is right there between the two streams. Then we have position C or segment C. Also from this position where the line is broken on the first stream to where the line is broken on the second stream, that makes segment D. And the last segment is segment E. In cases such as this, as the case we're just seeing in a few minutes ago, it is necessary to divide the exchanger into sections in which T versus Q line is a single straight line segment for each fluid in each section, just like we saw. For the case illustrated in figure 20.5, this will result in 5 separate sections known as zones. As we see here, zone A, zone B, zone C, zone D, and zone E. Label A through E in the figure. The design and performance of the exchanger would then follow a zone analysis, that is an analysis zone by zone that will consider each section or zone from A to E in figure 20.5 separately. That is to examine these temperature differences between stream 1 and 2. In these conditions, we will need to analyze zone 1 then I'm sorry, zone A, zone V, C, D, and E separately. In certain cases, most often, when there is a large temperature change for a fluid in an exchanger, the specific heat capacity of the fluid may change significantly, and TEQ line for a stream or both stream is curved, as shown in figure 20.6. That is, we might have a situation like this, where there is a constant heat capacity on the fluid on stream 2, and a change in heat capacity on the fluid in stream 1. Likewise, we could have a changing heat capacity on both fluids, on the hot fluid as well as on the cold fluid, gaining energy, gaining heat. This situation can also occur when partial condensation occurs in a stream containing condensable and non-condensable components. However, this situation is far more complicated and must be considered as a separate case. Comparing figure 20.6, this figure, and the analysis carried out in section for the countercurrent flow, in the book is section 20.11, it should be clear that since the TQ lines for at least one of the streams is not straight, just like we see here on the A diagram, on stream 1, the TQ line is not straight. Where are we? It should be clear that since the TQ line for at least one of the streams is not straight, the integration of equation 20.3 will no longer yield LMTD and equation 20.7. So equation 20.7 will not be the result of integrating this in case that CP is changing with temperature, as we see in scene number 1 on the left. For these cases, the usual practice is to integrate equation 20.3 numerically to give the appropriate form of equation 20.8. An alternative method is to approximate the curve TQ line as a straight line segments, and the LMTD for each segment can then be found, similar to a zone analysis. Figure 20.7 illustrates this method. So let's check on that. In here, we see this zone analysis. So instead of having 5 zones, we only have 2 zones, where we could see that T1 came in at this high temperature. And we see this is the real behavior, the curve, the solid curve is the real behavior of the hot stream. And this is the real behavior of the cold stream, this straight line between the incoming temperature of the cold stream and the exit temperature of the cold stream. A slight positive slope, very small positive slope. But to approximate this analysis to a zone analysis, an analysis by zones, then this curve was approximated to a straight line, and then is why you see the dashed line. And there was somewhere along the curve a partition, like you see there, a partition, where it was taken that in this partition there are Ti, this will be the temperature of the hot stream in position, this is position I, Ti, and the small Ti right there at Q1. Okay, and then from here, from Ti to T2, also you see a straight line. This is a simulated behavior from this I position to position number 2 for the hot stream. Likewise, the cold position is approximated as a straight line from Ti to this position right there, or rather, from Ti to T1. Yeah, this will be Ti, and this will be the original T1, right? So the difference will be the difference between these intermediate temperatures with respect to the real temperatures on both sides. That's why we see that on the first zone, like we see here, what will be the logarithmic mean temperature difference? We will have, see, if we can simulate 2 exchanges, let's just say, we partition the exchanger in two sides so that the hot stream is coming in not at T1, but it's actually coming in at Ti. That's where you see Ti right there. In a counter-current configuration, that will be Ti minus Ti, because this is a small Ti, is a Ti of the exchanger of the stream, the cold stream, leaving the exchanger on the same side. Ti minus Ti, and on this side we will have T2 minus T1. So the natural log will be Ti minus Ti over T2 minus T1. So this will be the procedure for a counter-current configuration, the LMTD in a counter-current configuration, when we have a graph that describes the behavior along the full length of the exchanger, but partitioned in zones. So this zone will be taken from the intermediate temperatures as if the exchanger, the hot stream, is coming in right there in this position, this Z position, and the cold stream is leaving right there. As you know, as is the exchanger having cut in two, and then one part of the exchanger is coming in and leaving in a portion of the exchanger, and another part of the exchanger is coming and leaving on the second portion of the exchanger. So now if we have this other zone, the difference will be what? T1 minus small t2, then we have Ti minus small ti, divided by a natural log of T1 minus T2, divided by Ti, this big Ti, divided by small ti, just like you see there, times the area of the second section and the overall heat transfer coefficient, which is assumed to be constant. That's what you see there, the same U. There is the same U right there. The area changes because this is another portion of the exchanger. It has a different area. Along this length has a different area. And this portion of the exchanger also has a different area. That's why you see A1. So at the end of the day, that gives Q1, this portion of the exchanger, and this other portion of the exchanger gives us Q2. So adding these two, then we'll have the full heat load of the exchanger, doing a zone analysis, an analysis by zones. In the derivation of LMTD given in section for counter-current flow, it was assumed that the overall heat transfer coefficient did not vary within the exchanger. Often this assumption is very good. However, for the case when streams undergo large temperature changes, the physical properties used to estimate the film heat transfer coefficient, especially liquid viscosity, may change greatly. That is for viscous fluids like oils, greases. Then the overall heat transfer coefficient along the length of an exchanger will change significantly. For this case, the analysis to determine the required heat transfer area becomes complex because the variation in U must be included in the integration of equation 20.3. Now we have to integrate 20.3, considering that U does change along the length of the exchanger. For the case when the change in U is linear or close to linear with amount of heat transfer Q, a modification of equations 8 and 9 can be made, and then we will obtain equation 10. What do we have in equation 10? We have a term, an average, you see this big part, an average of the overall heat transfer coefficient times the difference in temperature, the logarithmic mean of the product of these two parameters. So that would mean U2 delta T2 minus U1 delta T1 divided by the natural log of this product divided by this other product. That will give us, as you see there, U delta T with the big part LM, as you see right there. And in this equation, we have to multiply times the area in order to obtain the heat load of the exchanger. So this is the case when U changes and has a linear, the change has a linear behavior along the length of the exchanger. So if the behavior of the change in U is linear, in a way it's predictable, it has an slope that is predictable and constant, then you could use expression 10. Let's see this example. Low pressure steam at 160 degrees Celsius is used to heat very viscous oil from 30 to 65 in an exchanger located at the inlet to a pump. The amount of energy needed to heat the oil is 2.65 gigajoules per hour. Over the temperature range of the oil, the physical and transport properties of the oil are all constant, except for the viscosity, which decreases significantly as the oil is heated. Using this information, calculations show that the overall heat transfer coefficient at the oil inlet and outlet are 245, that would be watts, that is joules per second, over square meter per Kelvin. As you guys know, those are the units of the overall heat transfer coefficient. So in position 1, that will be 245 watts per square meter per Kelvin, and in position 2 will be 390 watts per square meter per Kelvin. For this exchanger, draw the TQ diagram, and calculate the heat transfer area required in the exchanger. Okay. So the information in the problem statement is represented in figure 20.3, where we have position 1, that you see in red, 245 watt per square meter Kelvin. Position 2, we see in blue, U2 is 390 watt per square meter Kelvin. It also is saying that low pressure steam at 160 is coming in, and we have very viscous oil heating from 30 to 65. So in the exchange, it does not tell us that it is a current configuration. The exchange located at the inlet to a pump. Unless we take this located at the inlet to a pump. So there is no clue in here that the exchanger has a co-current configuration, just like you're seeing here. But you're seeing that 160 is coming in on the opposite side of the exchanger and leaving on the side where the oil is coming in. So we're assuming that's one of the things you guys will have to do is to assume a counter-current operation. We already saw that counter-current operation will give us a greater delta T logarithmic mean. So in an exam, you guys don't need to resolve or to solve the problem using concurrent configuration, or even, asking in the middle of the exam what configuration should be considered. But you guys can automatically consider a counter-current configuration. So just like has been done in this example. In this example, it does not tell us at all if the exchanger is concurrent or concurrently configured. We only know that we have these two streams. So the author, Turton and his co-workers, already assume that it will be a counter-current configuration, just like you see right there. That would mean that this temperature difference is 130, just like you see there. And this temperature difference is 95. Para decirlo en español, y digamos recalcar, no vale la pena recalcar, que ustedes pueden asumir como futuros ingenieros que les falta probablemente un semestre o un par de semestres. ¿Cuántos aquí están a un semestre de graduarse? La materia integradora el próximo semestre y salen. ¿Cuántos de aquí están a un semestre de graduarse? Puede quizás escribir en el chat. ¿Y cuántos aquí están a 2 semestres de graduarse? Agradecer a sus comentarios en el chat. Normalmente en la clase de diseño hay un grupo de estudiantes que están a un semestre de graduarse y hay otros grupos que están a un par de semestres de graduarse, pero no están muy lejos. Parece que estamos 11 el que habla, sí. Entonces, si alguno de ustedes puede comentar cuántos semestres le falta para graduarse, se lo agradecería. Y si ya ha terminado sus prácticas profesionales también. Porque cuando salga a la industria, usted va a tener que, si está en posición de tomar decisiones, quizá al principio no, y con el tiempo va asumiendo responsabilidad porque eso es el curso de la vida. A nosotros eventualmente nos va a tocar jubilar, ustedes van a pasar a tomar esas posiciones que los jubilados pues dejan atrás y se les eleva a posición de responsabilidad y eventualmente ustedes van a tener que tomar decisiones en el lugar donde ustedes laboran. Un semestre ya se gradúa, bueno, le felicito Diego, un semestre, le felicito Brian, práctica culminada, felicito Brian, me alegro que las haya terminado. Muy bien, ahora tenemos otro comentario más. Muy bien, entonces, ok, eventualmente tiene que hacer su posición, como ingenieros tienen que hacer sus posiciones. Y un cálculo rápido, si usted necesita un intercambiador en la compañía donde se trabaja y tiene que hacer un cálculo rápido, se puede suponer de entrada que la configuración va a ser contracorriente. Es una suposición sana que la hace de entrada y si usted dimensiona el intercambiador, determina el área de transferencia después de estimar el coeficiente interno de transferencia de calor, el coeficiente externo de transferencia de calor y usa la fórmula para determinar el coeficiente global de transferencia de calor con los factores le llaman fouling factors, los factores es como, eh, eh, los factores eh, taponamiento sería fouling, no sé si, ¿cómo lo diríamos? Un factor de ensuciamiento sería quizá. Factor de ensuciamiento para el lado interno del intercambiador se llama fouling factor y factor de ensuciamiento del intercambio en el lado externo. Y eso ocurre. No sé si les he comentado a ustedes, pero en una fábrica café donde trabajé, donde se procesa café soluble instantáneo, el grano de café tostado y se produce café soluble instantáneo, ¿no? Mayormente se exporta. Similar a quizá el proceso que utiliza Sika, soluble instantáneo, que está aquí en la Carlos de los Menos, que es la compañía del café. Y en esta empresa, como tienen un evaporador enorme, ocurría que se tapaba el evaporador, se tapaba, literalmente se tapaba. Se iba construyendo interiormente en los tubos verticales del evaporador, se iba haciendo como, así como las personas que sufren de arteriosclerosis se les van tapando las venas con grasa, ¿no? Más o menos era una arteriosclerosis del evaporador, pero se iba tapando con este material orgánico que no era más que café seco en el tubo interior del evaporador, hasta que como una arteriosclerosis se tapaba el tubo, se tapaba. Y ya no pasaba más y se perdía esa área de transferencia. Ese es el fouling, digamos. Ocurre en un ensuciamiento, claro, ya es un ensuciamiento. ¿Por qué es ensuciamiento? Porque el café se iba secando en el interior del tubo y esa película de café seco en el interior del tubo hacía que caiga el coeficiente de transferencia de calor y se volvía pues el evaporador más ineficiente. Perdía eficiencia, digamos. Y peor aún cuando se tapaba un tubo, el área de transferencia equivalente al pi por d por la longitud de intercambio se perdía por completo. Entonces ya el evaporador no contaba con esa área, había que restarle la capacidad. Y si habían varios tubos tapados, todo ese conjunto de áreas sumadas se restaba a la capacidad original de intercambio de calor que tenía ese evaporador. En otras palabras, se perdía capacidad de procesamiento, capacidad de producción de café concentrado, de extracto de café concentrado. Entonces, ese fouling factor es una situación muy real, muy real. Del lado del vapor, casi no ocurre, porque el vapor se hierve, es el resultado de hervir agua blanda en un caldero. Del lado del vapor, del lado del vapor que entrega su calor latente, no ocurre esto. Del lado del fluido, si es un fluido que viene del proceso, un agroproceso y contiene material orgánico, esto es algo muy vívido, ¿no? Más aún el café, que es pegajoso en alta concentración, ¿no? Y efectivamente ocurre ese ensuciamiento interior, la película forma una caída significativa en el coeficiente de transferencia de calor, eventualmente cuando se tapa el tubo de un intercambiador o del evaporador, pues se pierde toda esa área de transferencia y el evaporador se vuelve ineficiencia y empieza a caer su capacidad de producción. Entonces, el fouling factor es algo muy real y es algo que debe de considerarse en los cálculos. Muy bien, estamos aquí. Ah, 245 en una posición, 390 y el diferencial de temperatura. Using equation 2010, Q, since we have this U is 245 and this U2 is 390, we have a difference in U. It appears to be linear. Then we can use this equation 10, where we have U2, which is some sort of an average value times the product of times this difference, this delta T2, minus the value for U1 times this difference, delta T1, over the natural log of this product over the natural log, over this product in here. And that's why we will see that. So A, we're solving for A because that's what it's asking. He's asking, so calculate, well, draw the TQ line and TQ diagram and then calculate the heat transfer area required in the exchange. So he's asking for the area. So since we know that Q is equal to UA delta T, logarithmic mean, and since we're going to use equation 2010, because now U changes in a linear fashion along the exchanger, so U delta T is going to be considered as a product. And when solving for A, because we're looking for the area of the exchanger, we will have Q over U delta T with the big bar Lm, where U delta T with the big bar Lm is going to be equal to U2 delta T2 minus U1 delta T1 and the natural log of the product of U2 delta T2 divided by U1 delta T1. There should be a 1 in here. See, there's a small mistake in the book. It should be U1 times delta T1. And you also see that delta T1 is right there, 130. Just as you see 130, and U2 is 95. So the values is actually corresponds to the delta T1. And delta T2 is U2 390 times 95. Correct. So these values are correct. It ends up being 34,384 watt per square meter. Why the units are in square meter and not square meter per Kelvin? Because we were already multiplying these times the temperature, and the temperature difference in temperature is in Kelvin. So the result of this product, since this is in watt per square meter Kelvin in the SI units, we multiply times Kelvin in SI units, we'll have watt per square meter. That's what we see right there. So it's about 34,038 kilowatts per square meter. So the area will be the heat load of the exchanger, which was expressed as 2.65 gigajoules. Gigajoule is 1,000 times bigger than a megajoule, if I'm correct. It's 1 times 10 to the 9. Is that correct? 2.65 times 10 to the 9 joules per hour. Divided by this watt is in joules per second. So there has to be a conversion in here, which is what you see there. 3,600 seconds per hour. So that this is also converted to joules per hour. And it can be canceled out. And since this is also divided by square meters, we'll finally end up with the units in square meters. So it's pretty much straightforward. It's not complicated. You guys have also seen probably this in fundamentals of heat transfer. Maybe not this case of U multiplied times delta T and the whole thing in an average fashion. But this formula, Q is equal to UA delta T, you guys probably did see this in fundamentals of heat transfer. So this is like a review. For the case of partial condensation from a gas stream containing non-condensables, the situation is even more complex because the temperature driving force and U may both vary non-linearly with Q. Okay. Additionally, the mass transfer of the condensable component to the non-condensable component to reach the cold surface must be considered. Such situations require numerical solutions that include the changing of physical properties, film, heat and mass transfer coefficients, and temperature driving forces throughout the exchanger, the exchange equipment. Many commercial software vendors including Heat Transfer Research, Aspen Technology, Chem Stations, and others provide programs to perform these calculations. That is, we're going to be limited to simple cases. Cases where the physical properties change, the overall heat and mass transfer coefficients change, and the driving forces change throughout the exchange. That is not going to be considered in this case, in this, let's say, in this review of heat exchangers. And also the author is pointing to the processing software that you see here. You guys have the Aspen Plus, and you probably will use Aspen Plus as you guys start working on your PFD. And then once you define your PFD, you start running your PFD to get the results, hopefully to get a recycle stream to optimize your process, and then do an economic analysis. Hopefully your process will be economically viable, and then you could present that. Okay, this is a table from Stephen Hall, Rules of Thumb for Chemical Engineers. This is, when was this? This is a 2018. So I do have some of the books I have are physical, mostly physical, and a few of them are through Kindle. Because when I started teaching this class, I didn't have, it was just, I was notified a few days before the semester started. So I have no time to buy the book and get it physically. So I did have to buy a few books via Kindle. So this particular book is via Kindle, and it shows a table 12.9 with the approximate overall heat transfer coefficients. And we will see that when we have, for example, the hot fluid is water and the cold fluid is water, the overall heat transfer coefficient in SI units will be between 850 and 1700. And for English or imperial units, sometimes all engineers call these imperial units, because the units actually came from the British Empire when Britain was an empire. And so they were called imperial units, the units of the empire. But now Britain is not an empire anymore, and these are just called English units. So in English units, it will be BTU per hour per square feet per degree Fahrenheit. And so on and so forth, it will be the different situations. Organic solvent with light oil, gases, and brine. Brine is a salt mixed with water, and it decreases the temperature to the melting temperature, and it increases the boiling temperature. So that's the purpose of a brine. So water and a brine, that will be the ratio, or the range, the U range, the overall heat transfer coefficient range. For heaters, this will be the situation. For evaporators, see if this is a common case where you have steam on one side, we have water on the other side. So the U average will be 31. We see that the average is just 2000 plus 4300 divided by 2. That gives us 3150 watt per square meters degrees Celsius. So when we study separators and we examine evaporators, which is not usually mentioned in books, I did find very limited information in a German book translated into English from some German authors, and they do mention certain information about evaporators and heat transfer coefficients and so on. Very interesting. And this is mostly from what I observed. So we have an example in the separator section, mostly from what I observed, what I saw in the books, and what I observed when I work at this coffee company. And we do simulate the calculations for overall heat transfer coefficient. Although this is very simplistic, and in real life, the calculations are more complex. But since this is a review of separators, not right now, when we finish heat exchangers, the review on heat exchangers. We're not going to go too deep, just deep enough for the understanding of how the exchange between the latent heat from steam exchanges heat with the cold stream coming in, and how that makes the fluid boil, the processing fluid boil, and there occurs a separation, a gas liquid separation, and so the processing fluid gets to be concentrated. And after being concentrated, and later on it is being dried, and that's why you end up with dried instant soluble coffee. That dried instant soluble coffee that you guys, or your parents purchased from supermarkets, it came from a concentrated solution of instant soluble coffee, a very heavy, it's a concentrated solution which came from an evaporator. So it's very interesting. So you actually may have been, eating, or if you guys like coffee in your houses, maybe some of you do, maybe not everyone, but some of you might like coffee. Well, that instant coffee came from a processing factory that had evaporator, extractors, centrifuge, and there were many equipments of unit operations. It's a very interesting process. It had many exchangers, pumps, and then on the side of the utilities, the boilers, big boilers, the cooling towers, then chillers, and then so on and so forth. Very interesting. It's a very interesting to watch and to observe a process like that. By the way, we went, nosotros nos fuimos a Montecristi con el semestre anterior, estudiantes del semestre anterior, y por lo menos voy a intentar, no otra vez a Montecristi, porque no quiero molestar a esta compañía que ha sido muy amable con nosotros, el café, 2 veces en el año, sino contactar con la Fabril. Y también tengo un contacto en Ales, donde yo trabajé, Industrias Ales en Manta, ¿no? Y la Fabril en Montecristi. A ver si nos dejan visitarlos a ellos, por lo menos 10 estudiantes, y el que habla, poderlos visitar, la Fabril o Industrias Sales. En Industrias Sales está la planta industrial, la refinería de la foto del curso que usted ve cuando usted hace clic en página de inicio. Usted ve esa es la foto de la refinería de palma, soya, girasol y canola de Industrias Sales. Eso está en Manta, en la instalación industrial que está sobre la avenida 113, a la entrada de Manta, ¿no? Y la planta de la Fabril está pues en la vía Montecristi Manta, ¿no? Ustedes que son de Manaví, algunos de ustedes o van y visitan Manaví o tienen parientes en Manaví o en Manta, se habrán dado cuenta dónde están estas plantas, que son enormes. Especialmente la planta de la Fabril es gigantesca. Entonces, voy a tratar en lo posible que nos autoricen una visita de por lo menos 10. Por eso les animo a que se esfuercen, que obtengan buenas notas para tomar los primeros 10, invitarles a ir una vez que acabe el semestre, después del examen final. Y si pueden los 10 bien, y si los 10 no pueden, continúen invitando hasta llenar la buceta con 10, y el que habla, para irnos a la Fabril. Temprano a las 7 de la mañana, parar en Cascol, comer algo quizá ligero, llegar a Fabril, visitar la planta un par de horas, ¿no? Ojalá la planta de refinación, que hay bastantes equipos de operación unitaria, y salir de ahí y regresarnos. Básicamente eso. Al final del semestre, próximo año, si Dios permite, después del examen final, que eso es la 3ª semana de enero, la siguiente semana. Entonces, para tenerlo presente, ¿no? Eso hicimos, pero no en la Fabril, sino fuimos al café hace unos pocos meses con los grupos de diseño de la clase anterior. Nos fuimos y la pasamos bien. Así que hay que tener presente, jóvenes, que Dios mediante hay esa oportunidad, ¿no? Okay. Overall heat transfer coefficient for condensers, this will be the range. If we have condensing stream with positive pressure, that's why you see pressure, it will be between 2000 and 4300. And if we have condensing steam under vacuum, which is usually the way evaporators work, so that the heat shock is very low on the evaporator, so you don't destroy the product on the other side. That would be between this range. Heat exchange equipment, design, and characteristics. Okay, these exchangers are the workhorse. Which exchangers? The shell and tube heat exchange. La configuración de tubo y carcasa, ese tipo de intercambiadores de tubo y carcasa. Dice, shell es la carcasa, tube son los tubos, que son muy comunes y dice que son el workhorse of the processing, el caballo de trabajo de la industria de procesamiento. Tenga en cuenta que el libro de Turton es un libro no para orientado hacia la agroindustria, a pesar que en la agroindustria se utilizan intercambiadores de calor, bombas, evaporadores, etcétera, centrífugas. Está orientado el libro para plantas químicas de procesamiento de químicos orgánicos o químicos inorgánicos, pero está orientada hacia eso. El libro entero está orientado para el procesamiento de químicos. Como hemos examinado al inicio de la clase, la dehydrotoluene hydrodealkylation, puede ser esa reacción toluene hydrodealkylation to produce benzene, ¿no? Eh, y hydrodealkylation, bueno, no, en este momento no sé cómo decirlo, la hidrodealquilación, si lo podemos decir, de tolueno para producir benceno. Hemos visto ese proceso en las figuras 1.3, 1.5, semanas atrás, ¿no? Al inicio de la clase. Y eso es una planta química. Y así, bueno, Turton se mantiene con ese proceso de manera consistente a lo largo de sus capítulos. Y es interesante porque así uno se familiariza con ese proceso. Ah, pero no está orientado el libro de Turton para plantas agroindustriales, como tampoco lo está el libro de Smith, ni el libro de Peters, ni el libro de Gavin Towler, ninguno de ellos. Estamos estudiando de libros que están orientadas al diseño de plantas químicas. Tenga presente eso. No tenemos libro, yo no tengo un libro conmigo ni de texto ni complementario que esté específicamente dirigido a plantas agroindustriales. Lo que se ha procurado hacer es enseñar, digamos, el contexto de esta clase, entendiendo, a pesar de que está de parte original de los autores orientado hacia diseño de plantas químicas, como el Aspen Plus también está orientado al diseño de plantas químicas y la librería del Aspen Plus contiene información para el diseño de plantas químicas. Aún así, se trata de aplicar el contexto de este libro para que pueda utilizarse en otros contextos como plantas agroindustriales. Nosotros no hacemos aquí ejercicios de plantas agroindustriales, pero estos ejercicios como, por ejemplo, el diseño de intercambiador de calor, también se puede hacer, se puede aplicar para procesos agroindustriales, como por ejemplo, calentamiento de una solución de café, de una solución de jugo de maracuyá y otros, ¿no? Es decir, estos principios son igual válidos para otro campo de la práctica, para otra aplicación, como la aplicación de plantas agroindustriales, ¿no? Ujú. Okay, so heat exchange equipment design and characteristics. These exchanges are the workhorse of the process industry, and an enormous amount of literature is available about the thermal and mechanical design of this type of which equipment, the shell tube exchangers. Many of the mechanical considerations are set forth in the standards of the Tubular Exchanger Manufacturing Association, which is TIMA, Tubular Exchanger Manufacturers Association. A brief summary of the key design considerations are given here, followed by a list of heuristics for choosing which fluid should be placed in the shell or tube side of the exchange. Nos vamos a ver recomendaciones o reglas de mano, heurísticas. ¿Qué fluido se recomienda en un intercambiador que esté dentro y qué fluido se recomienda que esté fuera? The main components of a shell and tube heat exchanger are shell and tube cover, tubes and tube sheet, channel and channel cover, baffles, inlet and outlet nozzles. A good review of each of these components is given by Mukherjee, and a summary of the results of this work are presented in the next section. The TIMA designation, Mukherjee aparentemente publicó en un journal en el año 98 bajo el título Effective Effectively design shell and tube exchangers. Ok. Entonces, hizo una publicación del diseño eficaz de intercambiadores de tubo y carcasa. The theme designation for shell and tube exchangers are given in figure 20.8. Eso es lo que vamos a ver acá. The notation for several examples of shell and tube exchangers are given in figure 20.9, que es la de acá. And some standard designs are given in figure 20.10, que la vamos a ver a continuación. 20.10. Ok, vamos viendo. Aquí podemos ver, vemos esto. Aquí podemos ver, aquí se alcanza a leer, dice front end stationary head type. Este es el cabezal del intercambiador. Este es el cuerpo shell types, los tipos de tipos de carcasa, literalmente, son los tipos, diferentes tipos de carcasa o el cuerpo del intercambiador. El cuerpo quiere decir el tubo que es usado como carcasa, ¿no? Y ese viene a ser el tubo exterior. Luego dice rear end head types. Estos son los cabezales que están en la parte posterior del intercambiador. Usted se dará cuenta, aquí tenemos tubos. Aquí se puede ver claramente en este tipo de cabezal hacia el final del intercambiador hay un tubo y es soldado aquí en esta pared metálica. Esta pared metálica se llama espejo. Y justamente, y mire este otro tubo, ese tubo se encuentra más adentro, este tubo se encuentra más afuera, viéndolo en corte, ¿no? Y aquí se alcanza a ver cómo el tubo pues sobresale un poquito de esta pared metálica, seguramente aquí está soldado, y como este tubo también que está más cerca de uno, se encuentra sobresaliendo un poquito. Este espejo es donde se sueldan los cuellos de estos tubos, y al otro lado, que es el cabezal de ingreso, usted ve también el espejo y ve los tubos soldados en el espejo. Aquí se encuentran soldados los tubos en el espejo. Acá también, soldados en el espejo. Entonces, de un lado, a través de la carcasa, el interior de la carcasa, llega al otro lado, al otro espejo, el tubo en donde va, por donde interiormente va a fluir el fluido de proceso. Afuera de los tubos, del lado de la carcasa, va a fluir el fluido que corresponde en la parte exterior. Y así ocurre esto. Usted puede ver, ¿qué más podemos ver aquí? Sí, se ve, es consistente. Vemos, tubos llegan y se sueldan. Tubos llevan y se sueldan aquí. En el espejo, este es el espejo de este lado, y de este otro lado, del lado del cabezal de ingreso, es el otro espejo que se suelda. Y eh, corresponden perfectamente. De modo que no hay inclinación en los tubos. Este va a ir perfectamente horizontal y terminar soldándose al otro lado. Perfectamente horizontal. En corte, se observa así. Usted ve los tubos soldados en el espejo. Mire que usted puede retirar este cabezal. Implica, según el dibujo, que eso está apernado. Pasa un perno, pasa una tuercota y seguramente en el círculo del cabezal, en el círculo de esta brida, esto es una brida, se ve el corte aquí, acá hay otra brida. A lo largo de ese círculo de la brida, usted puede ver esta línea aquí, por donde va a pasar el pernote. Se aprieta con una tuercota y se hace un torqueo en cruz hasta que se aprieta todo. Del lado del cabezal, lo mismo se hace del lado del cabezal posterior. Aquí está la brida del cuerpo, la brida del shell. Esta es la brida del cabezal posterior. Y esto, aquí usted ve la línea. Por ahí debe de pasar los pernos y apretarse con torque, con un torquímetro. Es una palanca que tiene unas indicaciones numéricas y eso ayuda a dar una cierta libra-pie en unidades inglesas o newton metro si está en unidades del sistema internacional. Mire esta configuración AES. Configuración A quiere decir que el cabezal es el tipo A. Dice, no alcanzo a leer aquí, Channel Unremovable Cover. No alcanzo a leer aquí que dice esta configuración. Luego dice AE es One Pass Shell. Quiere decir que esta configuración El A es este, tiene removable core. Usted puede ver la tapa. La tapa aquí también es apernada. Se aperna con esta sección y esta sección se aperna con la carcasa. En la carcasa, donde están soldados donde está el espejo y soldados los tubos, como usted puede ver aquí. No en este cabezal. Este cabezal se puede desapernar y sacarlo del todo. Y eso sirve si usted quiere limpiar interiormente los tubos pasando un cepillo de tubo en tubo para limpiarlo en caso que tenga algún tipo de depósito orgánico. Eso es bastante útil. Al otro lado igual. Saca los pernos, saca todo este cabezal y queda el tubo. Usted va a ver ahí los tubos que se encuentran aquí. Seguramente los tubos de este lado no están soldados, de tal manera que usted desaperna esto y saca toda esta tapa y que se exponen los tubos al exterior. Y usted puede pasar un cepillo de lado a lado. De este lado usted puede desapernar la tapa, se abre esto y queda pues este cabezal totalmente descubierto, el interior, digamos, y usted lo puede limpiar. La configuración AE, como vimos en eso. AE. Y luego nos dice que es S, que es un floating head with a backing device. Es exactamente el intercambiador que, que nos implica esto. Pero vemos, este es la cabezal flotante, le dicen. Es un tipo de diseño de cabezal flotante. Eh, para ser sincero, no conozco las minucias del diseño de intercambiadores, el diseño mecánico de intercambiadores de calor y qué implica un diseño mecánico de cabezal flotante, ¿no? Como en lo físico, qué exactamente es flotante, ¿no? O quiere decir que los tubos no están soldados, o los tubos, o que el cabezal se pone y se saca y los tubos no están soldados al cabezal, como se puede apreciar aquí. Yo entendería que es algo así, porque si usted saca los pernos y estos tubos están soldados aquí, usted no podría sacar el cabezal. Pero si los tubos no están soldados aquí, usted sacaría los pernos, retira la tapa y los tubos quedan expuestos, ¿no? Es lo que tendría que ser. En este caso es el cabezal flotante. Estas otras dos configuraciones, BEM y AEP, corresponderían a BEM y la otra nos dice que es AEP, sería AEP. El P quiere decir el cabezal posterior sería outside packed floating head, otro tipo de cabezal flotante, dice outside packed, empacado exteriormente. No sé si esto quiere decir que se arme el cabezal y luego se coloca en posición, puede ser. Este es el cabezal outside packed floating head. La verdad no conozco las minucias, pero esa es la denominación del diseño mecánico. Y acá nos dice son standard Shell and Tube Heat Exchanger Designs, como vemos el CFU, el AKT, el AJW, el acá, diferentes. Vemos como el cabezal del AJW tiene ambos cabezales iguales en la parte frontal y posterior, pero están girados 180 grados. Entonces, la boquilla de ingreso del uno está en un costado, tiene la boquilla en el lado posterior girada 180 grados, como se puede ver aquí. Del lado de la carcasa tenemos una boquilla de ingreso y dos boquillas de salida. Muy bien. Vemos aquí Shell and Tube Exchanges. Fundamental process data include flow and temperature information for the hot and cold streams. One of the values is calculated based on the other five to close the heat balance. The radio buttons identify the unknown. Entonces vemos aquí una hoja de Excel en donde ya está preprogramado la información que se ingresa de tal modo que hace automáticamente un balance energético y determina lo que se necesita por decir. Si el flujo total del lado frío es 25.000 libras hora, con estas condiciones de temperatura en Fahrenheit en unidades inglesas, ¿no? Y estas condiciones de presión en unidades inglesas manométricas, ¿no? PSIG, manométricas, diferencial de presión, y el coeficiente de resistencia al ensuciamiento, fouling resistance, que son unidades inversas a las unidades del coeficiente de transferencia de calor. En unidades inglesas sería pie cuadrado hora de grado Fahrenheit sobre BTU. Y vemos nosotros que del lado caliente, para estar en balance con el lado frío, se requeriría un flujo total de 15.000 libras hora. La temperatura de 100 a 74 sería la caída de presión 5 PSI. Y la presión de ingreso 75, aquí igual manera del lado frío, la caída de presión 10 PSI, el ingreso a 60 PSIG. Y el factor de resistencia o el factor de ensuciamiento 0.003, o sea, 3 veces más que en el lado frío. The following is a list of heuristics. Okay, son recomendaciones. Heuristics son recomendaciones. For the design of shell-and-tube heat exchangers that is modified from a Bell and Mueller. Aquí tenemos este par de investigadores, Bell and Mueller. Wolverine Engineering Data Book, Germany, son ingenieros alemanes. En Wieland, que esa es la compañía Aktiengesellschaft, que es AG. Muy bien. Like any set of heuristics, these should be used as guidelines and not as immutable laws. Some heuristics may seem to be contradictory, and the final choice is often a compromise between conflicting phenomena, with the deciding factor being which design is at least expensive, is the least expensive. Son recomendaciones. Choice of tube side fluid. If one stream has a much lower film coefficient than the other, the lower coefficient stream should be placed in the shell so that the extended surface of the fins can be added to the outside of the tubes to increase the surface area. Therefore, if a gas and a liquid are to exchange heat, the gas will normally go on the shell side. For high and low viscosity liquids, the low viscosity fluid is normally placed in the tubes. Entonces vemos eso, que el fluido de baja viscosidad va en los tubos y el fluido que tiene bajo coeficiente de transferencia va del lado de la carcasa. If a fluid is highly corrosive, this fluid should be placed in the tubes. This heuristic is due to the corrosive fluid needing to be in contact with a corrosion-resistant alloy, which is usually expensive. It makes the best economic sense to have the tubes and connecting piping made from this alloy. On the other hand, the shell and baffles and tie rods can be made out of less expensive material like carbon steel that is only in contact with the shell side, less corrosive fluid. If the temperature and pressure conditions for one of the fluids require the use of specialty alloys, that fluid is placed in the tubes for the same reason given for highly corrosive fluids. When one fluid is at much higher pressure than the other fluid, that fluid is placed in the tubes. Since higher pressure requires thicker walls, it makes sense to place a high pressure fluid inside the tubes, while the shell can be designed for a lower pressure fluid. If one fluid causes severe fouling or scaling, that fluid is placed in the tubes. But a U-tube, a type U design is not used. Since straight tubes can be mechanically cleaned relatively easily, it makes sense to put the fouling fluid in the tubes. Interesante que nos explica que cuando un fluido, como es una solución orgánica, no puede ser una solución diluida o concentrada de jugo de maracuyá, de café soluble, en un intercambiador, cuando los tubos están rectos y van de lado a lado, es fácil limpiarlo. Pero si el intercambiador tiene una vuelta en U, tiene tubos que dan vuelta en U interiormente, esa vuelta en U es muy difícil de limpiar. Entonces, si es un fluido que tiene un severo problema de ensuciamiento, produce ensuciamiento, el tipo de intercambio U-tube no es el más recomendado. Fixed tube sheet arrangements are not designed to be able to relieve thermal-induced stresses. One heuristic is to use fixed tube sheet exchanges only when the inlet temperature of the two streams differ by less than 55 Celsius. Importante que el diferencial de temperatura no sea más allá de 55 grados cuando los tubos están fijos soldados en ambos lados del intercambiador. Fixed tube sheet exchangers have been used for temperature differences up to 110 with roll expansion joints for moderate pressures in the shell. Es decir, cuando ya pasa de 55 el diferencial de temperatura de los fluidos en el intercambiador, se pueden usar juntas de expansión que permiten que el tubo se expanda por el diferencial de temperatura y no haya un daño mecánico en el intercambiador donde se expande el tubo y el tubo está soldado en ambos lados y eventualmente algo cede, algo se rompe, ¿no? Eso es lo que ocurre. Se colocan juntas de expansión cuando la presión va por debajo de 10 bares. U-tube bundle provides comprehensive solution to the thermal stress problem on the tube side because they contract and expand independently of the shell. But tube sheet stresses still exist. If one fluid is very viscous, this fluid should be placed on the shell side, provided that by doing so, the fluid is in the turbulent regime. Vemos como el número de Reynolds en el lado del shell es mayor a 100. Para considerarlo turbulento. If turbulent flow conditions cannot be achieved in the shell, the viscous fluid should be placed in the tubes. Y vemos nosotros, bueno, se cancela todo. Reynolds number is inversely proportional to viscosity. Quiere decir que mientras mayor sea la viscosidad, menor es el número de Reynolds. Mientras menor sea la viscosidad del fluido, menos viscoso, aproximándose al comportamiento del agua, el número de Reynolds es mayor. Mientras mayor es el número, la viscosidad, el número de Reynolds, pues, como ocurre en fluidos como el aceite, aceites en general, el número de Reynolds se cae y puede llegar incluso al régimen laminar, que no es lo deseable, porque en el régimen laminar empiezan a ocurrir los depósitos, el ensuciamiento en los intercambiadores. If one fluid requires a low pressure drop through the exchanger, if this fluid is placed on the shell side of the exchanger, in general, the shell side pressure drop is lower than the tube side pressure drop. In addition, as discussed in section 22.1, that is in shell configurations, many different shell configurations are available that lower the shell side pressure drop. Up to this point, there has been no discussion on the value or determination of the overall heat transfer coefficient. U is a combination of several heat transfer resistances that act in series. And these resistances are illustrated in figure 2024 for both planar and circular geometries. Figure 2024 is a wall is shown separating two fluids at different temperatures. Y aquí podemos ver, aquí tenemos la pared, esto habrán visto en problemas de fundamentos de transporte de calor donde ocurre un diferencial de temperaturas interior y exterior. Si el fluido caliente está en el interior, el fluido frío en el exterior, pues va a haber zonas donde cae la temperatura. Aquí tenemos una transferencia de calor por convección hasta la pared, por conducción a través de la pared y otra vez por convección hacia afuera de esta pared, ¿no? Cuando tenemos viene a ser el flujo de calor de izquierda hacia la derecha, el fluido caliente hacia el fluido frío. En un tubo en donde uno de los dos está a mayor temperatura, ya sea el fluido interior o el fluido exterior. Si por decir es el exterior, entonces habría transferencia de calor por convección del exterior hacia la pared, por convección a través de la pared y por conducción, perdón, por convección desde fuera hacia el límite de la pared, conducción a través de la pared y convección otra vez desde el interior de la pared hacia el centro del tubo, ¿no? Aproximadamente. Entonces vemos aquí el Q de conducción, en el caso de la pared, en donde la resistencia es L sobre KA, el Q de convección, HA, diferencial de temperatura, donde temperatura infinito es la temperatura bastante lejana a la temperatura de la superficie. Y en el caso de este lado, el Q de conducción a lo largo de la pared curva de un tubo sería menos Ka delta T de R, donde R es la resistencia L sobre Ka, y el Q de convección es HA delta T a sí mismo. Tenemos aquí. Una revisión de estos temas que se vieron en fundamentos de transporte de calor. For steady state operations, the amount of heat transfer through each layer of resistance must be the same. By writing the basic heat flux equation across each resistance and eliminating the intermediate temperatures, an overall expression for the heat transfer in terms of the bulk temperature driving force, which is used in the exchange design equation, is obtained. So here we see for circular tube geometry with a single wall and a scale formation on the inner and outer surfaces. Similar analysis gives. Entonces, en esta situación, balance energético, mire que va del hot fluid, del fluido caliente al exterior, puede ser vapor condensando, al cold fluid, el fluido frío al interior, puede ser agua que se está calentando. Aquí tenemos, también nos dice que tenemos formación de escamas, scale formation, al interior y al exterior de la superficie del tubo. En el fluido caliente tenemos el factor de resistencia exterior. El fluido caliente transfiere calor por convección. Luego tenemos el factor de resistencia. Va a ser igual al factor de resistencia, el fouling factor, el factor de ensuciamiento exterior, y va a ser igual a conducción a través de la pared, y va a ser igual a la convección otra vez al interior del tubo hacia la posición más alejada del tubo. Aquí vemos unos comentarios de lo que aparentemente está, como usted puede ver, aquí está faltando una A, porque las A finalmente van a tender a, si no hay mucha diferencia, van a tender a cancelarse. El RFO está expresado aquí, pero acá también lo expresan. El RFI está expresado aquí también. Y aquí faltaba un signo igual. Exacto, aquí faltaba un signo igual que está en rojo. Where the subscripts O and I refer to the outside and inside of the tube respectively, and the resistances due to fouling are given in terms of an effective fouling heat transfer resistance, as you see there. Outside resistance and inside resistance respectively. Lo que usted observa aquí, outside resistance y aquí inside resistance. Inside quiere decir dentro del tubo y outside por fuera del tubo. Y esta delta X es el espesor de la pared del tubo. The form of equation 2021 differs from that derived for planar geometry because for circular geometry, the cross-sectional area through which the heat flow changes from the outside to the inside of the tube. By eliminating the intermediate temperatures and rearranging, the following working equations for circular geometry can be derived. Q is equal to outside overall heat transfer coefficient area of the overall outside area, the wetted perimeter, delta T of the bulk, that will be the bulk temperature of the fluid, that will be equal to inside overall heat transfer coefficient, the area of the inside wetted perimeter times delta T of the bulk inside of the tube, 2022. And we'll also see that U outside and U inside have these definitions, where the U outside is 1 over the film transfer coefficient on the outside resistance, this ratio accounting for the convection to the wall, then the inside resistance, and finally the inside heat transfer coefficient to the power of -1. And this is the definition for the inside. This is the outside, this is the inside. Where DI and D0 are the inside and outside diameters of the tube or pipe, respectively. From equations 2023 and 2024, it is clear that for circular geometry, the overall heat transfer coefficient must be defined with respect to the specific surface, but that the product UA is the same no matter what surface is chosen. So that UI, AI, which is the inside film transfer coefficient times the inside area is equal to the outside overall heat transfer coefficient and outside area. It should also be noted that equation 2022, which is this equation, we see UAO is equal to UAI, probably because these two cancel out. It's saying that it should be noted that equation 2022 was derived from a specific location where delta T bulk is known. If the temperature difference between the fluids varies with location, as it would in most heat exchangers, then an appropriate average temperature difference should be used. Se debería usar un delta T bulk, un delta T del cuerpo, del promedio de temperatura del cuerpo del fluido. Si ese cambia a lo largo del intercambiador, pues eso se debería utilizar un tipo de promedio entre el ingreso y la salida. ¿Qué más tenemos acá? Unas tablas. Ok. Vamos a detenernos. A ver si nos detenemos. Acá. The analysis given in section 20.1 and all the limitations discussed in section 20.1 still apply. Thus, the general working equation for heat transfer between fluids exchanging heat to tube walls becomes, entonces vemos U0, A0, delta T, Lm, F, este es el factor de corrección, is equal to UI, AI, delta T, Lm, F, el factor de corrección. Entonces, cómo se iguala el intercambio de calor, la carga de calor, de un intercambiador que me imagino que tiene intercambio perfecto, que todo el calor va de afuera hacia adentro, denotados por los subíndices exteriores e interiores. Recuerde que este F tiene su fórmula, realmente lo incluimos para mencionar esto mañana. Hay una fórmula para el cálculo y un diagrama para el cálculo de F, el factor de corrección, ¿no? Según la configuración del intercambiador. Bueno, jóvenes, eso es por ahora. Gracias por su paciencia, a los pocos de ustedes. A ver si mañana, Dios mediante, nos conectamos de 7 a 8, solamente de 7 a 8. Continuamos con esta discusión y el día martes, si terminamos mañana o terminamos el martes. Y eso sería todo. Parece que he tenido apagado. No funciona mi cámara. Yo creo que eso sería todo por hoy. Que tengan una excelente noche y nos vemos pues, Dios mediante, mañana a las 7. Así que gracias, jóvenes. Que tengan una excelente noche cada uno de ustedes.
Gracias,
Gracias,
profe.
profe, cuídense.
Hasta luego. Muchas gracias.